Now, it's also important to note that stress is a vector. It has not just a magnitude, but also has a direction. Gravity is down. That's pretty important. If gravity were sideways, life would be totally different. So stress is a vector, and that is very important, especially if you're an engineer. Different materials handle stress in different directions very differently. Now, if you remember from physics, any vector can be decomposed into the perpendicular and parallel components. We call the perpendicular component normal stress, because normal is a synonym for perpendicular. The parallel component is shear stress. So if you have a stress coming in at some angle to your desk, for example, part of that is straight down against the surface of the desk, and part of that is straight along the surface of the desk. We can use these two equations to break down the stress into the normal and shear components, where if we have some angle relative to the surface that we care about, whether it's a fraction plane, whether it's a bedding plane, whether it's the surface of the ground, the surface of your desk, the surface of your hand, whatever the stress is being exerted on, it's at some angle, and so we can figure out the normal and the shear components of it. If, on the off chance, that incoming stress is perfectly perpendicular to the surface, theta equals 90. You can still plug it in, and it turns out that shear stress will be 0. Sine of 2 theta is 0 if theta is 90. The normal stress will be the whole amount, because the cosine squared of 90 is 1. So it still works no matter what angle the stress is coming in. Now finally, we'll cover Newton's third law, the law that says for every action there is an equal and opposite reaction. And we use this to simplify three-dimensional cases, which in geology is everything, because the world is three-dimensional. So we can basically use Newton's third law and simplify things down into fewer dimensions when we're examining them, because if we have a stress from the left, whatever it's being exerted on is exerting a stress back to the right in the opposite direction. So you can see in this diagram, for example, the different stresses labeled A, B, C, and D, and on this point in the center, if there's a stress from the bottom, there's a stress being exerted back. It's exactly negative of the original stress. Now, this kind of diagram kind of looks like a big watermelon or a blimp or a zeppelin or something like that, with a chunk cut out of it, is called a stress ellipse or a stress ellipsoid. And this is used to describe the stress orientations on some object, the object being like at the center of it. And the length in the three axes, x, y, and z, are related to the strength of the stress. So sigma 1, the biggest stress, so that's the long axis of our ellipse. Sigma 3 is the small one, so it's the narrowest part. And sigma 2 is something in between. These sigma 1, 2, and 3 are always orthogonal, means perpendicular, means normal, so they're all 90 degrees from each other. And they're all normal stresses. So they're the perpendicular to the planes that contain zero shear stress. So if you have your stresses coming in different orientations, you have to break them down and find the normal stresses to get these. Fortunately, that's not something that we actually spend a lot of time doing. It's fairly easy to figure out the orientation of sigma 1 and sigma 3 in geology by looking at what's going on usually, and then using a few simple equations or diagrams or tools. Now, this is something that's going to look really complicated, but then we'll simplify it for you. But if you have stresses coming in at different angles and you break them down into the perpendicular and shear components, so you have stresses coming in from 3 different directions, you break them all down, all 3 of them into their normal and shear components. Those components will have these labels because they'll be in the X, Y, and Z directions. And the cube here is our object that all the stress is happening to. We can make a little diagram or a little table showing the 9 bits of stress that are happening. Looks really complicated, and like we're going to have to do lots and lots of calculations because there are 9 different stresses. However, if it's not moving, these 6 are all going to cancel out. The 2 in blue are opposite of each other. If it's not moving, they've got to be exactly equal, or it will be moving in one direction or the other. Same with the 2 green, same with the 2 red. So all the shear stresses cancel out or are 0 when the body's at rest. That only leaves 3 that we have to worry about. Those 3 happen to become sigma 1, 2, and 3.